Okay, hello. We're going to go over the homework from section 10.3 on parametric equations. Let's do it. I have a pair of parametric equations, x equals t squared, y equals 5 minus 4t. The directions for number 1 were find dy dx. What is dy dx? It's the slope of the tangent line to the parametric curve. And basically, the way to do this is that dy dx is just dy dt over dx dt. The reason for this is some combination of common sense and basically just the chain rule. Of course, if you treat dy and dx as real things, infinitesimals, this is the infinitesimal change in y over the infinitesimal change in x, then of course this just makes complete sense because derivatives just behave just like fractions. So maybe that's the best way of understanding this. Anyway, what is the derivative of y with respect to t? It's just negative 4, and the derivative of x with respect to t is 2t, and so we get this formula, negative 2 over t. And what we have here is a formula which takes as input a t value, and the output is the slope of the tangent line to the parametric curve at the point determined by that t value. Okay, so maybe I'll just leave that alone. Let's do some more. Number 9 gives you this parametric equation, x equals 2 cosine theta, y equals 2 sine theta, and there were a whole bunch of steps that you had to do for this problem, and let's kind of talk out some of the logic behind what we're doing via this problem. In some sense, it's a silly problem because this is just a circle. So, of course, x equals cosine theta, y equals sine theta is sort of by definition the parametrization of the circle given a unit circle and a point which has been rotated theta degrees counterclockwise from 1, 0. Then, by definition, the coordinates of this point are cosine theta comma sine theta. That is actually just the modern definition of cosine and sine. So, of course, this pair of parametric equations is, by the definition of sine and cosine, the parametric equations for the circle of radius 1. And since that's true, this pair of parametric equations will be a circle of radius 2. Okay, so in some sense this is kind of a pre-calculus problem, and it is a little bit silly to do any calculus at all in this problem number 9 because I already, in some sense, know everything there is to know. Here is 2 comma 0, and I can plug in various points. I don't know, plug in pi over 2, and you get 0 comma 2. Ooh, marker's dead. So all these markers might be dead. There we go. This point is 0 comma 2. That's at t equals pi over 2, etc. And this curve is being traced out in this manner. In particular, we are told that we are supposed to be caring about t equals pi over 4. At t equals pi over 4, well, you can just plug in, I shouldn't say t, I should say theta. Of course, there's no difference, theta, t, whatever variable you use. Sometimes people just use theta when it comes to trig functions because we want to think of it as an angle, but whatever. Point is, if you plug in pi over 2 here, you're going to get root 2 over 2, so, and root 2 over 2 for the other one as well, so this is just root 2 comma root 2. Alright, I mention pi over 4 because that is the theta value that the problem is going to ask me about. And I kind of just already know the answers to whatever possible problems they might ask. The slope of that tangent line is definitely going to be negative 1. And I know that based on just circle geometry, although my line looks a little bit bad there. This line will have slope 1 because it's going from 0, 0 to root 2 comma root 2, and so the perpendicular line will have a slope which is negative 1. Still though, it's nice to see my calculus bear this out, so let's go. let's calculate, in general, the slope of the tangent line to this curve, dy dx. Well, again, it's going to be dy d theta over dx d theta. And what is the derivative of y with respect to theta? Derivative of 2 sine theta is 2 cosine theta, and the derivative of x with respect to theta is negative 2 sine theta. Okay, anyway, the 2's cancel, and we just get this formula, negative cotan theta. Okay, so I'll put a little box around this, because what we have here is a formula for dy dx. Again, you plug in a theta value, and the output of this function is the slope of the tangent line to the curve at the point determined by that theta value. Okay, and just to make sure that you get it, the book then asks you to specifically to compute dy dx at theta equals pi over 4, and so you then just plug pi over 4 into your formula, and the cotan of pi over 4 is 1, so this is negative 1, and that's exactly what I expected to get in this problem based on the common sense geometry. Okay, good. Part 1 of this problem is over. Part 2 says, hey, also do this other thing. And it doesn't really give you this kind of big picture. It just says, find d squared y dx squared for this parametric curve. What is this d squared y dx squared? Well, it is, in my opinion, unfortunate notation for the derivative with respect to x of dy dx. And this is kind of tricky because we have a lot of different things going on here. We have y, we have x, we have theta, and we're differentiating sort of with respect to all those different things. So what is this saying? Well, probably the best way of thinking about this is it's saying, hey, take dy dx, which is the slope of the tangent line to the parametric curve, and differentiate it with respect to x. In other words, we're taking the derivative of this thing, so we're asking what is the rate at which this thing is changing. Okay, so what is the rate of change of the slope of the tangent line to the curve? But, and this is hard, but I said all this in class multiple times, so maybe everybody gets it now. But if you were absent or something, what this is saying is take the derivative with respect to x of dy dx. In other words, for an infinitesimal change in x, what is the change in dy dx? And in fact, maybe this sort of simplest way of thinking about what this is saying, yo, what is the change in dy dx with respect to a change in x? That's what it means to differentiate one thing with respect to another thing. We're basically saying, hey, what happens if you increase x by a tiny, tiny bit? What is the change in dy dx? And therefore, what's the ratio between those two infinitesimal changes? In other words, if you want to bring it back to the geometry of the curve, I have a certain point on this curve. I have the slope of the tangent line to the curve at that point. And this thing that I'm being told to compute is really asking the question, hey, let x get a tiny bit bigger. What happens to dy dx? And therefore, this computation can be seen as the answer to the question of what is happening to the slopes of the tangent lines to the curve as x gets a little bit bigger. And if we find that shifting over in the positive x direction by some infinitely small amount makes the slope of the tangent lines decrease, in other words, if this turns out to be negative, then it means that the slopes of the tangent lines are getting smaller. And if the slopes of the tangent lines are getting smaller, we say that the derivative is decreasing. If the derivative is decreasing, then that means that the curve is concave down. Okay, so in general, this is an answer to, is this curve concave up or concave down? Because, what does it mean to be concave up or concave down? Sure, it means tangent lines, lie below the curve if it's concave up, tangent lines lie above the curve if it's concave down, but an alternative sort of definition of concave up, say, is that the tangent lines to the curve, as you move to the right, are increasing. So a curve is concave up. In fact, this is the definition of concave up in many textbooks, including our textbook. that a function is concave up if the derivative is increasing. And here the derivative is going from big negative to 0 to big positive. Okay, so good, let's do it. How do we do it? Well, this is kind of a little bit tricky, right? Because we are differentiating something, dy dx, which depends on theta, with respect to something else, x, which also depends on theta. And so actually, if you sort of understand everything that's going on here, then you will see that we are in the same position as we were when we were doing dy dx. What made this computation dy dx not totally obvious? What made it not obvious is that x and y are each functions of theta. Theta is the real variable. Theta is the independent variable. Theta is the thing that is changing. Y depends on theta, and x also depends on theta. Well, here we are in the exact same position. dy dx depends on theta, and x depends on theta. So since these two things both depend on theta, we have to do the same thing that we did before. And just like we had to differentiate y with respect to theta and x with respect to theta, here we have to differentiate dy dx with respect to theta, and we have to differentiate x with respect to theta. Okay, so if you totally get that, good. If you don't get this, this is a complete repeat of what I did in all classes, but anyway, I'll just do it again. What some people find helpful in this situation is to temporarily use a new variable. So let's just temporarily let z be dy dx. So in other words, I am kind of abstracting away from dy dx for a moment and just giving it its own variable name for no particular reason. And of course, what is dy dx? Something that depends on theta. Since dy dx is something that depends on theta, you can just think of it as a single thing that depends on theta. So let's just call that thing z. And therefore, if going back to here, if what I want is the derivative with respect to x of dy dx, I can kind of rewrite that as the derivative with respect to x of z. Because I've temporarily named this z. In other words, this is just dz dx. And that makes this problem seem exactly like the original problem, and it is. So what is this? It's just dz d theta over dx d theta. And therefore, what is dz d theta? It's just the derivative with respect to theta of z. And what is dx d theta? It's just the derivative with respect to theta of x. Okay, and of course z was just our temporary name for dy dx. And so really what we need to do is we need to take the derivative with respect to theta of dy dx and the derivative with respect to theta of x. Okay, so good, that's the last time I'm going to go into this level of detail. Now let's actually just do the problem. So what is d squared y dx squared? It's the derivative with respect to x of dy dx. In other words, it's the derivative with respect to theta of dy dx. So we have to take the derivative with respect to theta of negative cotan theta over dx d theta, which is negative 2 sine theta. Okay, and I know that the derivative of cotan is negative cosecant theta, and so cosecant squared theta rather, over negative 2 sine theta. And so this formula I end up with is I have 3 negatives, and I end up with negative 1 over 2 sine cubed theta. Okay, and then the final thing we had to do for this problem is to specifically calculate d squared y dx squared at theta equals pi over 4. And if I do that, I end up with negative 1 over 2 times what is sine of pi over 4? Well, it's root 2 over 2, but maybe it's even easier to just think of it as 1 over root 2 cubed. And so that's negative 1 over 2 times, if you cube root 2, you get 2 root 2. So it's 1 over 2 root 2. So the 2's cancel, and that's negative 1 over root 2, which is just negative root 2. Okay, so ran out of space a little bit here, but the answer to the other part of number 9 is negative root 2 is the numeric answer to what is the second derivative of y with respect to x at pi over 4. Okay, what does this mean? Again, it's just a repeat of exactly what I said in class. This means that at theta equals pi over 4, which lands us at root 2 comma root 2. Not only is the slope negative 1, but the slope is changing at a rate of negative root 2. Which means, for a small change in x, in other words, inch forward ever so slightly in the x direction, which means moving like from here to here, okay? Let x get a little bit bigger. If x gets a little bit bigger, then this is telling me to expect negative change in the slope of the tangent line to the curve. And of course, that's exactly what the picture shows us, right? Starting at the point theta equals pi over 4, and if x gets a tiny bit bigger, what's happening to the slopes of the tangent lines to the curve? Well, they're becoming more steep. The slope of the tangent line to the curve at theta equals pi over 4 is already negative 1, and it becomes a bigger negative number. In other words, the slope decreases as x moves to the right. And therefore, this problem didn't ask me to conclude this, but I therefore conclude that this curve is concave up at theta equals pi over, concave down. Because the second derivative is negative, this curve is concave down. And you can just see clearly that in quadrant 1, the circle is concave down. I didn't need calculus to tell me that, but of course the calculus is supporting what my own eyes are telling me. Okay, great. The last thing, which I also said in class that is potentially confusing, is that even though as I move to the right, the slopes of the tangent lines are decreasing, the curve itself is actually moving to the left. So it is a fact of this particular, if you go into the details of this parametrization, which were not part of the calculus problem that you were supposed to do, you will see that as theta increases, in fact, we move counterclockwise around the circle. And so in fact, you might be saying, if you just ask the question sort of casually, hey, what's happening to the slope of the tangent lines? Well, what's happening to the slopes of the tangent lines over time is that they're actually increasing. They're going from a big negative to a 0 to a small positive to a big positive. Okay, so even though with respect to theta, the slopes of the tangent lines are increasing, with respect to x, the slopes of the tangent lines are decreasing. But if what I am interested in is whether the curve is concave up or concave down, then I need to ask my questions with respect to x. Because when I ask whether the curve is concave up or concave down, I'm asking questions about the curve, not the particular way in which the curve is traced out. So the details of the parametrization are sort of washed out when I ask this question. And actually you see for this problem that dx d theta is negative. If you give me a first quadrant angle, sine of that first quadrant angle will be positive. So this negative coefficient means in fact that dx d theta is negative here. What is the meaning of dx d theta being negative? Well, it means that as theta increases, x decreases. Of course that is true, because as we move counterclockwise through the first quadrant, theta is getting bigger and x is getting smaller because we're moving this way. Okay, and so so even though the slopes of the tangent lines with respect to theta are increasing, the slopes of the tangent lines with respect to x are decreasing. And that's another sort of explanation for y, we divide through right here by dx d theta. You're sort of canceling out to some extent the details of the parametrization by asking the right question. Okay, that was way too long. Back in 1 second for the rest. Okay, I apparently assigned another one of the exact same problem, which is maybe a little bit overkill. Anyway, let's do it. This time without comment. dy dx. I have to calculate is dy d theta over dx d theta, and the derivative of cosine is negative sine, so that's going to be sine theta over dx d theta will be 1 minus cosine theta. Sure, that's just right. Yep. And anyway, there you go. There's my formula. And specifically, they then asked what is dy dx at theta equals pi. So I just plugged pi in here. Well, sine of pi is just 0. Cosine of pi is negative 1, so that's 2, so that's just 0. In other words, there is a vertical tangent, a horizontal tangent at theta equals pi. Okay, part 2 of the question asked again for d squared y dx squared. So now we recognize that that means what is the derivative with respect to x of dy dx? And we know that that means what is the derivative with respect to theta of dy dx, which is this thing. So actually this is a little bit of a drag. And over dx d theta, which we already saw to be 1 minus cosine theta. Maybe I should just write that. Dx d theta. So that's the logic of what's going on. Okay, so now I just need to differentiate this. I guess I'm just going to use the quotient rule, I suppose. So derivative of the first, derivative of sine is cosine, times the second, 1 minus cosine theta, minus the first, times the derivative of the second, and the derivative of 1, hold on, I think I've done something terrible here. Oops. Okay, bad video. I just made a complete, no. Everything is fine. I take it back. Everything's fine. I got a little confused because the derivative of x is actually just y, so that was confusing me. I think this is all good, right? This is x, this is y. Great video here. Dy d theta over dx d theta. Dy d theta is in fact sine, and dx d theta is 1 minus cosine. That's all good. And now I'm taking the derivative with respect to theta over dx d theta, and dx d theta is indeed, yeah, okay, so everything's fine. So derivative of the first times the second minus the first times the derivative of the second, and the derivative of 1 minus cosine theta is in fact sine theta. So that's sine theta. This is just me doing the quotient rule so far, over 1 minus cosine theta quantity squared. And then this whole thing is over dx d theta, which is 1 minus cosine theta. Okay, so we end up with, we end up with 1 minus cosine squared theta minus sine squared theta over 1 minus cosine theta cubed. But then this is a little bit of a silly problem because I guess this is just 0. How is this possible? Oh boy. No, man, another algebra mistake. Cosine theta minus cosine squared minus sine squared. Okay, so then this is cosine theta minus cosine squared theta plus sine squared theta, but of course that's just 1 over 1 minus cosine theta cubed. So that ends up being cosine theta minus 1 over 1 minus cosine theta cubed. Okay, so one of those are going to cancel, and I guess I just get negative 1 over 1 minus cosine theta quantity squared. Man, not 100% confident of my answer there. I made a bunch of mistakes along the way even, but I can quickly check this. And if I quickly check this, because I have the answer to every problem in the world, this was number 14. I bet I'm right. I just am right. Negative 1 or more. Okay, good. So this is my formula in general for d squared y dx squared. Of course, it's a little bit unsatisfying because we're not going to actually do the problem, or we're not going to actually graph these parametric equations. I believe that this is like a cycloid or something. I'm not really sure. Okay, so anyway, final thing to do that they tell me to do is plug in theta equals pi. And if I just plug pi into this formula, I get cosine of pi. It's negative 1, so 1 minus negative 1 is 2, so that is negative 1/4. And there's just the answer to this problem. Okay, good. Surely now you certainly get it. And I'm not sure how many more of these problems we really needed to do, but we're going to do 5 more. So 24 is a complete repeat of what we did in class. So x equals t cubed minus 6t, y equals t squared. And the questions they ask, find the equations of the tangent lines at the point where the curve crosses itself. At the point where the curve crosses itself. So if you don't have any technology and you've never done a problem like this before, you might be just completely lost. How am I supposed to know where this curve crosses itself? Well, the only solution is to just get in there and like do some work. So let's just do everything that we know how to do. What do I notice about this curve? I notice that the y coordinate is always positive. I can also very quickly see that as t goes to infinity, these are both going to infinity. As t goes to negative infinity, x goes to negative infinity, and y goes to infinity. And then I also can factor t cubed minus 6t and see that I can take out a t, leaving me with t squared minus 6, and I can factor that even more as t minus root 6 t plus root 6. And what is that useful for? Well, it's useful for me to make a sign chart of x and y in terms of t and see that my x coordinate changes sign at negative root 6, at positive root 6, and it's actually going to change sign negative, positive, whereas my y coordinate is simply always positive. So this is helpful if my goal was to graph the function. And okay, the curve, and the curve is starting to come into focus a little bit because I see that t equals 0 is important, t equals root 6 is important, t equals negative root 6 is important. If I plug in 0, I get 0, 0. If I plug in root 6, I get 0, 6. And if I plug in negative root 6, I get also 0, 6. So that means that this curve, I'm just going to tell you already, looks kind of like this. There's a point 0, 0, cha, 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 cha. There's a point 0, 6, cha, 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 cha. And where do I start? I start at time negative infinity, at negative infinity, comma infinity. In other words, I start kind of way up here. And I think what's going to happen is, by the time I get to time negative root 6, oh, also my x coordinate is negative, my y coordinate is positive. I'm going to cross through this point, 0, 6, at time negative root 6. Then my x coordinate is going to briefly be positive again until I get to time 0, at which point my x coordinate is going to be negative until I get to root 6, and then my x coordinate is going to be positive. And so I'm expecting some kind of shape like this, which is exactly like the shape that we graphed in class when we did our intro example, but This time it's been kind of rotated 90 degrees or something like that. Okay, so therefore, what have I just learned? I've just learned curve crosses itself. Okay, curve crosses itself at the point 0, 6, and that's at time root 6 and time negative root 6. Okay, great. Now, what's the actual problem? The actual problem says, what are the equations of the tangent lines at the point where the curve crosses itself? So, now we finally are going to do some calculus, because we haven't done any calculus yet. What is dy dx, which will give me the slope of the tangent lines of the curve? Answer, well, I just do it, right? It's dy dt over dx dt. dy dt is 2t, and dx dt is 3t squared minus 6. Fact. Okay, can I do anything with this? I don't know. I guess that's just 2t over 3. Never mind simplifying it, because I just don't think it's worth it to simplify. Because that's my formula, because what was now my goal? My goal was to find the slopes of the tangent lines at specifically these points, because those are the points I care about. Okay, so let's do it. What is dy dx specifically at t equals root 6? Answer, well, I just plug in root 6 for t, and I get 2 root 6 over, plug in root 6 here, and that's 6, so 18 minus 6 is 12, and so that is root 6 over 6. Great. Okay, so whatever that number is, that is the slope of the tangent line to the curve as I come through the second time. And what is dy dx at t equals negative root 6? Well, if I get 2 times negative root 6 over, but I still down here get, when I square negative root 6, I get 6, so 18 is 12. So this is negative root 6 over 6, which kind of makes sense because this curve is completely symmetrical. And so this picture is making sense. And, the problem asks specifically for the equations of the tangent lines to the curves. So they go through 0, 6. So I guess it's going to be like y equals negative root 6 over 6x plus 6, and y equals root 6 over 6x plus 6. Okay. Good. 4 problems to go. Be back in 1 sec. Okay, let's do this pretty quick. These problems, 29, 33, and 34, all ask for you to find find points of horizontal and vertical tangency. Okay, let's go. Here, this one's pretty silly, I think, because if I want to find the slope of the tangent line to the curve, I just do it. dy dx is dy dt, so that's 3t squared minus 3 over dx dt, which is negative 1. And so this is just going to be 3 minus 3t squared, which of course you can write as 3 times 1 minus t squared, so 1 minus t, 1 plus t. And therefore, if that's the slope of the tangent line to the curve, it's never going to be infinity. So I'm going to have no vertical tangents. And when am I going to have a horizontal tangent? Well, I'm going to have a horizontal tangent to this parametric curve whenever the slope of the tangent line to the curve is 0. And since this is the formula for the slope of the tangent line to the curve, we see that this happens at t equals 1 and t equals negative 1. And I guess that's all I have to do. It did say points. So at t equals 1, I am at 0, comma. If I plug 1 in here, I get 1 minus 3 is negative 2. And at t equals negative 1, I get that x is 2. And y is negative 1 and 3 is 2. So I think that is good. We did that problem in most classes. Okay, 33. Let's do this one now. So let's start with just computing dy dx. What do I get? Well, it's dy d theta. I guess I'll just write that. Dy d theta over dx d theta. Dy d theta derivative of sine is cosine. Dx d theta derivative of cosine is negative sine, so I get negative 2 sine. Yeah. So this is negative 2 cotan theta. That's just my answer. Okay. Well, maybe we should just kind of make a graph of negative 2 cotan theta just for, I just know what cotan looks like. Cotan is that one. That looks like that. So negative 2 cotan theta is going to be upside down, and so we have something that looks like this, and of course that's just pi, and I guess if I want to go all the way to 2 pi, then this is just what upside down cotan looks like. So what have I just graphed? I guess the horizontal axis is theta, and the vertical axis is this formula, which is dy dx. So, all right, this will tell me the slope of the tangent line to the curve anywhere. What was the task? The task was to find the horizontal tangent lines and the vertical tangent lines. So if I want to know where the horizontal tangents are, I need to know when this is 0. So when is negative 2 cotan theta 0? Well, it just is at pi over 2 and 3 pi over 2. So answer, theta equals pi over 2, and theta equals 3 pi over 2. And where am I at theta equals pi over 2? I guess go back to the original again. I am at, cosine pi over 2 is 0, so I'm at 4, comma, 0. And at theta equals pi over 2, cosine of is also 0, so I'm also at 4. Sine of 3 pi over 2 is negative 1, so negative 2. And where am I going to have vertical tangents? I'm going to have vertical tangents when this slope is like infinite. Okay, so that's going to happen like at basically theta equals 0 and pi and 2 pi, etc. So let's just say theta equals 0 and theta equals pi, because this whole thing is going to repeat every 2 pi, of course. So, all right, where am I? At theta equals 0, cosine 0 is 1, so that's 6, comma, negative 1. And when theta equals pi, cosine pi is negative 1, so that's 2, comma, sine of pi is 0, negative 1. Okay, so that's the whole problem. We stop there. Of course, I also just happen to know this is an ellipse. Okay, that can be seen easily by just subtracting, right? We get x minus 4 over 2 is cosine theta, and y plus 1 is sine theta. And since cosine squared theta plus sine squared theta equals 1, we can then eliminate the parameter, and we see that this is, it's just x minus 4 squared over 4 plus y plus 1 squared, some people like to put the 1 there, equals 1, is the equation of this curve with the parameter eliminated. So what is this? It's an ellipse which has been moved 4 to the right and down 1. So 1, 2, 3, 4, and down 1. There's the center. X has been stretched out by a factor of 2. And y has been stretched out by a factor of 1. And so what we get is this ellipse. And this is the point 6, comma, negative 1. This is the point 2, comma, negative 1. That's the point 4, comma, 0. And that's the point 4, comma, negative 2. And it's exactly matching up with what we got there. Okay. Running out of time here, I have 2 more problems to do. Here we go. Yet another problem which asks you to find the places on this curve with horizontal or vertical tangent lines. Let's do it. Okay, well, step 1, just find dy dx. What is it? It's dy d theta over dx d theta. What is dy d theta? This you might want to write as for cosine theta quantity squared, just so it's a little bit easier to differentiate using the chain rule. I see that this is the derivative of 4 something squared is 8 something back inside for the derivative of the something, which is negative sine theta. So I had to do the chain rule for dx d theta, but dy d theta, derivative of sine is just cosine, so I just get 2 cosine theta. Okay, the cosines cancel, and I just get 1 over negative 4 sine theta. That's just right. Okay, and now comes the question, where do I have horizontal tangents? And the answer is none, because this derivative is never 0. Where do I get vertical tangents? Oh. Hi. Oh, kids downstairs. Also, you might be a little bit, you could have potentially gotten this wrong by thinking that, there was a horizontal tangent whenever dy d theta is 0, but of course that's not quite correct. You really do have to treat the entire formula dy dx simultaneously, because, when cosine is 0, I don't have a horizontal tangent. Because it's canceled out by the cosine in the denominator. Alright, whatever. When do I have vertical tangents? I have vertical tangents whenever this is 0. That happens at theta equals 0, theta equals pi, etc. And because then the denominator will be 0, and so the slope of the tangent line will be like infinite. So that's why I have a vertical tangent. If I plug in 0 for theta, what do I get? Cosine 0 is 1, so this is 4, comma, sine of theta 0, so I get 4, comma 0. But I think if I also plug pi in here, cosine pi is negative 1, but I also end up with 4, comma 0. So it seems that there's only one place where there's a vertical tangent. All right, most people would just stop with that problem and not to do anything else. But of course, we know from our experience in pre-calc C that cosine theta is always between negative 1 and 1, fact. So what about cosine squared theta? Well, it's always going to be between 0 and 1. Because if you square something between negative 1 and 1, it will be between 0 and 1. Thus, 4 cosine squared theta will be between 0 and 4. And thus, I've just proved to you that x is going to be between 0 and 4. Also, sine theta is between negative 1 and 1. 2 sine theta is going to be between negative 2 and 2. And thus, y is going to be between negative 2 and 2. Can I easily eliminate the parameter here? Yes, I can, because I'm sort of experienced with this. I know that if I take x equals 4 cosine squared theta, that I want to replace cosine squared theta, this is the technique, with 1 minus sine squared theta. Why is this a good idea? Because I know what sine theta is. Sine theta is y over 2. So I get this, and x is therefore 4 times 1 minus y squared over 4, or maybe even more simply, 4 minus y squared. Alright, so that is making me feel really good, because if I go to graph this, well, what do I know? I know that this curve stays between 0 and 4 in the x direction, and between negative 2 and 2 in the y direction. So there's some kind of like little box, rectangle, that this curve, square in fact, that this curve stays inside. And what is this curve? It's just sideways parabola, negative leading coefficient, and vertex here at 4, comma 0. If you plug in 0 for x, you will see that happens only, well, it may be just simpler to plug in 2 or negative 2 for y, and that gives you x equals 0. And so we're just up here, man. That's 0, 2. That's 0, negative 2, And what we have is this sideways parabola, and this parametric equation actually just starts somewhere. Let's see, at 0 we're here, and we just go that way, jump, 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 jump. And so it of course makes complete sense that there will be a vertical tangent at 4, 0 and no horizontal tangent. Okay, one more problem left. This is taking forever. Last problem. (39) says, this is the first problem in this homework that explicitly references concavity. X equals 2t plus lnt, y equals 2t minus lnt, 2t minus lnt. Okay, directions. Find the intervals in which the curve is concave up or concave down. First of all, let's just notice that t can only be positive because you can only take the natural log of something positive. All right, how do I find where this curve is concave up versus concave down? Well, now we know what to do, right? What we need to do is to find the derivative with respect to x of dy dx. That is going to be the question that answers are the slopes of the tangent lines to the curve getting bigger or smaller with respect to x? Okay, so how do we do this? First, I need to compute dy dx. So what's dy dx? It's dy dt, which is 2 minus 1 over t. Yeah. And dx dt is 2 plus 1 over t. And so maybe that's just true. So if I get a common denominator, that's 2t minus 1 over t all over 2t plus 1 over t. So really that's 2t minus 1 over 2t plus 1. Alright, so that's the formula for the slope of the tangent line to the curve. Now I need to know what is the rate at which that derivative is changing with respect to x. And so we've already seen, so I won't redo the explanation, that this is the derivative with respect to t of dy dx over dx dt. And so I need to take the derivative with respect to t of this formula that I got in the first step, 2t minus 1 over 2t plus 1, and all of that is over dx dt, which is, I guess, 2 minus 1 over t. Okay, so let's do this. I'll just use the quotient rule. Why not? So derivative of the top, which is 2, times the bottom, 2t plus 1, derivative of the top times the bottom, minus the top, so 2t minus 1, times the derivative of the bottom, which is 2, all over the bottom squared, 2t plus 1 quantity squared. And all of that is over this, which is in fact like, well, I guess it's like 2t minus 1 over t. Yikes. Okay. Well, I guess I'll just go here, right? What do I end up with? 4t plus 2 minus 4t, that's going to be plus 2, algebra, all over 2t plus 1 quantity squared, and all of that is over 2t minus 1 over t. And so I think I end up with 4 over 2t plus 1 squared divided by, so therefore times the reciprocal, which is t over 2t minus 1. So that's not exactly what I was expecting, but anyway, there it is. Here's my formula. It's 4t over 2t plus 1 squared times 2t minus 1. Okay, what is there to say about this formula? Well, it's some complicated rational function, but of course this is using all the things I know from pre-calc. This is always positive. So really, there is a sign change at 0, and at t equals 1/2. And so this is going to be quadratic e. Here's 0, here's 1/2, and these are t values I'm considering. And here's what I'm here to tell you, that this is going to be plus minus plus. I have just made a sign chart for d squared y dx squared. And great. By the way, don't forget that negative t values make no sense. And so really nothing happening to the left of 0 is relevant. Therefore, I'm now ready to say that my curve, since the slopes of the tangent lines to the curve are decreasing on the t interval from 0 to 1/2, that my curve is concave down on that interval and concave up on this interval. And so if I'm ready to answer the following question, the answer to this is that the curve, which I'm not even going to attempt to draw, is concave down on t from 0 to 1/2, and the curve is concave up on t from 1/2 to infinity. And that is, in theory, something which would help me graph this curve if I so desired. There is therefore a point of inflection at that point when t is 1/2. Okay, goodbye.